Good morning, ladies and gentlemen, and welcome to the SAIEE Nuclear Chapter webinar on Small Modular Reactors, Review of Molten-Salt Reactor Projects. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. And by default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. However, attendees will not be able to chat with each other, but we encourage you to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Nuclear Chapter playlist. You will find the registration link in the chat box. Please register. It is free, so you'll receive notifications when it's been uploaded. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to our host today, Dr. David Nichols, who is the chairman of the SAIEE Nuclear Chapter and was appointed as the chairperson of the board of the South African Nuclear Energy Corporation in January 2020. Prior to his retirement at the end of December 2018, he was a chief nuclear officer at Eskom. Internationally, Mr. Nichols was the chairman of the IAEA Technical Working Group on Light Water Reactors from 2010 to 2016, and is currently the co-chair of the IAEA Technical Working Group on Nuclear Power Plant Operations. He was a member of the WANO's post-Fukushima design review team from 2012 to 2018. Over to you, David.
Thank you very much, Minx. I'm just here to do introductions. I'm looking forward to this presentation as much as the audience is, because the molten salt reactors are things that I like the idea of them. I'm just not quite sure how they work sometimes. It's the interesting reactor. It's the one where you melt the fuel in the coolant, just as a part of plan. The presenter is going to be Derek Wolfart, who I've known Derek since 1988. Would that be Derek? About then? 87, 88, when you came back from the States?
Yes, 87, yeah.
He's got a BSc and MSc in nuclear engineering from the University of Tennessee, an MSc in paleontology from the University of Witwatersrand, and a PhD in applied mathematics from the University of Cape Town. So this guy has more brains than I've got. And he's got 30 years experience. He has in his life, he was in Eskom, he did his postgraduate work in Eskom, he did Eskom in the States, then he went off and worked in Belgium for Westinghouse in Brussels for some years. Then he came back and was Westinghouse's rep here, and now he's with Lesedi, one of the main nuclear engineering company in the country. So with that, I'm going to pass across to Derek, and I will leave the screen and listen with interest. Derek, the floor is yours.
Okay, let me share my screen. Are you able to see my screen?
Yes, please proceed.
Yes.
Okay, so good morning, everyone. Today we're going to do a review of small modular reactors. So first, we'll do a brief review of what a small modular reactor is. We'll look at advantages and limitations. Then we will look at some of the design options with molten salt, small modular reactors, and look at the current projects around the world where small modular reactors are being developed. So SMR is a small modular reactor, typically defined to be smaller than 300 megawatts. Although Rolls-Royce in the UK are building a 500 megawatt or designing a 500 megawatt reactor, which I do not consider small anymore. The main idea is that these reactors are manufactured under controlled conditions in factories, and one ends up with the economy of multiplicity. So not the economy of scale as in the big PWR and boiling water reactors, but the nth unit of these small reactors then becomes very affordable. You could categorize them as large reactors for large grids, like the PWR X300 that's under construction in Canada. Smaller ones for small grids, 70 megawatts or multiple units of 100 megawatts. And then off-grid applications, the 5 to 10 megawatts, where the competition is really diesel generation in the remote areas. All these small modular reactors have in common that they passively cooled and they're inherently safe. So they cannot undergo meltdown as in a big PWR. They're all designed so that the laws of nature, without the need of electrical power, can cool them down and keep them safe. Because they generally have reduced or fewer operating parts, they lead to reduced operating and maintenance costs. And there is a ideal application of these small modular reactors in synergy with renewables to provide carbon-free baseload. Some of the designs, one can operate multiple SMRs with a single operating team, also leading to some savings. So the IAEA has issued a handbook on small modular reactors, and they've categorized them in 6 categories. The first are the water-cooled SMRs, and the land-based ones. The second are water-cooled marine-based on the barges. And the third grouping is the high-temperature gas reactors. And Dave, in previous webinars, have presented on those 3 groups. Then there's another seminar coming on the fast neutron spectrum SMRs. Today we'll look at the molten-salt reactors in a bit more details, and then later on we could focus on the micro modular reactors, of which there happens to be one under development in South Africa called the PCMR, the Power Cell Modular Micro Reactor. Computer is just a bit slow. So molten salt reactors, the current designs are very innovative and promising. And as Dave hinted, the liquid fluoride or chloride salt acts as both the coolant and the fuel. So the fuel is dissolved in the salt. So unlike a PWR where the coolant is and moderator is water, but the fuel are in the fuel assemblies, in the molten salt reactors, it's the same thing. The coolant is the fuel. And the idea of core melt cannot occur because the core is already melted in the molten salt. So quite a different concept. Their designs mitigate a lot of the risks of other reactors. They operate at high temperatures, which leads to improved plant efficiency. And some of these high temperature applications lead to very valuable industrial applications, which I'll mention a little bit later on. So the key point I just want to make again is that the coolant is the fuel. And so uranium, plutonium, or thorium is dissolved in the salt. The picture that I show there is the Copenhagen Atomics. They have a 2-loop system. The first loop is the primary loop that contains the fuel and the coolant, and then the second loop is another secondary salt loop, and they offer heat, so they offer high temperature gas, high temperature steam for various applications. So there are many variations. Some of the molten salt reactors use spent nuclear fuel to get started with, like this one. And then they breed uranium-233 from thorium for a longer-term fuel supply. So molten salt has several advantages. The salt expands as it heats up, and so there's a very strong negative reactivity coefficient. So it's self-regulating. You would never get a runaway nuclear reaction. They operate at near atmospheric pressure. So unlike the pressurized water reactor where you have to prevent the water from turning into steam, you don't need heavy pressure vessels, very expensive pressure vessels, as well as all the regulations and rules, the ASME rules around pressure vessels for nuclear power stations. So that's a big thing that leads to affordability for molten salt reactors. So the high outlet temperature can produce carbon neutral hydrogen fuels, fertilizers. They can be applied for desalination and district heating. Typically, they're designed so that if something goes wrong, say the main circulating pump stops, the salt is drained from the core into a tank where it freezes and cools itself. So it's no longer in a critical configuration, and the nuclear reaction stops. Very simple, without any moving parts typically. There are some limitations as well. High temperature molten salt is highly corrosive, and that needs to be dealt with. Circulating pumps develop leaking seals, and since the fuel is dissolved in the coolant, that coolant gets circulated through heat exchangers and possibly pumps and valves, and all that equipment gets contaminated and would have to be remotely maintained. I'll say some more about how those limitations are overcome later on. So a molten salt reactor was operated in Oak Ridge in the late 60s. It was called the Oak Ridge Molten Salt Reactor Experiment. Reached first criticality on 1st of June in 1965. And it was the first reactor in the world to run on uranium-233 by 1968. The uranium-233 came from thorium that were bred in other reactors and then inserted in this molten salt reactor. So it had that innovation of the salt being the carrier for the fuel and acting as the coolant. It operated successfully for 13,000 hours at full power and was finally shut down in 1969. In order to mitigate the corrosiveness of the molten salt, they used a very specialized steel, Hastelloy-N. And they used graphite to be the moderator, and they used a special graphite to prevent the ingress of molten salt into the graphite, which is an issue that people need to deal with. And they experienced problems with the pump seals at this experiment, but the experiment was largely considered to be successful. So some of the modern designs to overcome the corrosion problem, the tendency is to use ultra pure salts, oxide-free salts, so that there's no possibility for corrosion in the loop. The pump seal leak issue is solved by a canned pump, so there is no seal, much like what the nuclear submarines use, and the Westinghouse AP1000 reactor also uses. So the Nuclear Energy Agency has issued a dashboard for ranking or assessing the status of SMRs in the world. You know, there's more than 70 different SMR projects, and they looked at licensing, siting, financing, supply chain, engagement with stakeholders, and the status of the fuel. So for each of these, they've developed 6 qualitative criteria. And so I'm just giving an example here for licensing, because licensing relates directly to the maturity of the design. So the criteria they use for licensing is that there's no information available. Second level is there's evidence of pre-licensing activities with the NRC or the Canadian regulators. The third level is that license applications have been submitted. The fourth level is the design is certified by the licensing authority. The fifth level is the license to construct is issued. And the final level is the license to operate is approved. So they have similar type of qualitative criteria for the other categories, but I'm not going to go through those here. So in this dashboard, they list 8 molten salt projects around the world. And I added Copenhagen Atomics at the bottom also. So the projects are undertaken in various countries, the US, Canada, UK, France, even United Arab Emirates, and 2 in Denmark, which is a non-nuclear country. And thermal power ranges from 60 megawatts up to 1,100 megawatts. So there's a full range of sizes for these molten salt reactors. And the big advantage, of course, is the high temperature, outlet temperature, which ranges from 550 to some 700 degrees Celsius. And we mentioned earlier that there are fast spectrum SMRs, and also amongst the molten salt reactors, there are some fast spectrums, but the majority of them operate at thermal neutron energies. So let's start with the first one, which is the FLIBE Energy, LFTR, the lithium fluoride thorium reactor. It's 600 megawatts thermal power, will operate in the thermal spectrum for neutrons, and it will use low enriched uranium and thorium. This is a United States project, and there you can see that the dashboard rating of it. You can see there's some progress in licensing and fuel supply chain financing, and quite a bit of engagement has taken place. So they've done some pre-licensing work with the NRC in the United States, the Nuclear Regulatory Commission. There's no new news or information about the siting. They've got some financing, $7.2 million in 2018, and they got one of these DOE vouchers for supply chain development from the Department of Energy, and that's their Nuclear Innovation Fund, and they're issuing vouchers. I couldn't find out how much money is involved with each voucher, but these people did get a voucher. They've had quite extensive engagement with their stakeholders, holders in civil society, and they also got, for the development of the Fuel 2 vouchers from the Department of Energy, and that will be done in partnership with the Argonne National Lab and the Pacific Northwest National Laboratory. The next one to talk about is the Moltex reactor in Canada, and this one is specifically targeted for burning recycled spent fuel pool. And so The SSRW stands for Stable Salt Reactor Waste Burner. So here you see the dashboard. They have done quite a bit of work in licensing. Well, not so much in licensing, but in the siting aspect of it, and public engagement, significant. And they've engaged with possible suppliers in the supply chain side of things. So they've completed phase 1 of the Canadian Safety Committee's vendor design review process. The site has been selected at the New Brunswick Power's Le Preux site. There's already a CANDU reactor operating at that site. And the idea is then to use the used spent fuel from that CANDU reactor in this molten salt reactor. They've got multiple funding from private sources and public sources. They also got some DOE vouchers and working with the Argonne National Lab. The Spanish company IDOM has invested in this project. So did Atkins Realis, the former SNC Lavalin. And they're partnering with the Canadian National Labs for using the CANDU spent fuel in this reactor. So that's one of the big benefits, is that these reactors are designed to use and reduce nuclear spent fuel. Next one is the Moltex Flex. Those two come, and this one is in the UK, but they're related to the previous development. And this one is graphite moderated, which is no surprise when you're in the United Kingdom. And the unique thing about this is that the coolant and the fuel salts are in separate loops from each other. So this coolant doesn't mix with the fuel, and therefore the coolant stays clean and do not have any decay products in there. There is no moving parts in the primary loops of this. It's all operates by convection. And the flex part of it comes from the fact that there will be some 6 molten salt tanks for storage, which provides flexibility for applications, different applications, as backup to wind and solar and for other industrial applications. So again, on licensing, there's not much information. Citing, there's not much information. They got a grant to do salt graphite research at Manchester University. They signed up with Jacobs to develop an experimental facility, which is being operated at the moment. Quite extensive interaction with government officials and public in the UK. And they recently got a $1.6 million award from the UK to develop the fuel. Next one is a French initiative, and this is one of those smaller molten salt reactors that can be placed within a standard shipping container. And so this one will operate in the fast spectrum, but the fuel has not been defined yet. So licensing is just very early. There was an early meeting with the French nuclear safety authorities. There's no information on siting. They did get $10 million from the French government, the 10 million euros. And they've signed a contract with a French company, Assystem, to develop a digital twin. And they're operating the first silicon carbide molten salt loop with the Mersen Group company. And for fuel, they're collaborating with the French company Robotel. We now move to the two Danish initiatives. There's the compact modular salt reactor. This is one of those ones where they put several units on a barge, multiple units, and they will also use low enriched uranium. You can see their dashboard there. In terms of licensing, they've made progress with the American Bureau of Shipping that approved the barge, but they still need nuclear licensing, which hasn't been done yet. They've signed MOUs for deployment in Norway, Indonesia, Philippines, and Vietnam. So there is some progress on siting. They're getting extensive funding from the Danish state and from venture companies. And in terms of supply chain, they've entered into a consortium with Korea Hydro and Nuclear Power and Samsung Heavy Industries. And they have various research programs ongoing in Denmark and in Sweden and elsewhere in the EU. And they've come to an agreement with KEPCO in Korea for the fuel production in Korea. And we now move on to the IMSRR from Terrestrial Energy. It stands for Integrated Modular Salt Reactor. So similar to what David talked about before, where you get integrated pressurized water reactors with everything within one vessel. This is the molten salt version of that. It will operate on low enriched uranium. They've done progress in licensing. They're busy with phase 2 of the Canadian Nuclear Safety Council's licensing process, and they're in the pre-licensing phase with the United States Nuclear Regulatory Commission. They've been shortlisted as a candidate for an atomic energy site in Canada and Idaho National Labs in the United States. They've got $35 million from public and private sector funding, and they've signed various agreements, one with Icon for construction, Hatch for project management, Siemens for the turbine supplies, and it's graphite moderated, so they've signed up with Fraser Nash, a UK consultancy firm, to help research graphite options. And they've come to an agreement to obtain uranium from Orano in France, and this contract has been signed with Springfields, which is the Westinghouse fuel plant north of Manchester. The next one, Thorcon, is another one of these projects that will be placed on a floating hull. The head office is in the UAE, but it's really, the deployment is aimed for Indonesia. There will be 2 modules in this hull. It will be floated into a dry dock and then ballasted to the seabed or to the floor of the dry dock. The 2 reactors will operate for 4 years, and one will be in operation and one will be in cool down. So one will cool down for 4 years and then removed and replaced by a fresh one, while the other one then goes into the cool down mode. Also low enriched uranium option. Licensing very early. They've only issued a consultation paper to the Indonesian regulator. On siting, they've identified one of the islands in Indonesia. They have established a $1.4 billion investment fund in Singapore, which will be released once the project is approved. It's not released yet, but the fund exists. And they've signed various agreements with Indonesian, Korean, and Spanish manufacturers. They also got a voucher from the US Department of Energy to develop the molten salt fuel. we're getting to the last couple now. Horizon 1 is a Dutch initiative. And again, in this case, they avoid mixing the fuel salt with the coolant salt. And the concept here is to use canisters with fuel in it. And these canisters can then be inserted into the core and removed from the core. So it's also intended to use spent nuclear fuel as a Kickstarter fuel and then breed thorium to get uranium-233. It's, as you can see on the dashboard, it's little more than a concept. There's no information on licensing. They have had discussions with the Dutch utility for placing it on the Borselen site, where there's already a nuclear reactor operating. They did get significant funding, $12.5 million from the EU, from public and private investors. And they've entered into a consortium with the Dutch Nuclear Regulatory Group and several universities. They've got agreements with Electricité de France, and when they've access to a fund for developing recycling opportunities of spent nuclear fuel for reactors. Get to the last one, also from Denmark, Copenhagen Atomics. This one is not on the SMR dashboard, but I had an opportunity to visit them a year and a half ago in Copenhagen, and they're making significant progress. It's a little different from the others. It's a heavy water moderated molten salt reactor. It will use spent fuel to kickstart then a thorium breeding cycle. It fits into a 40-foot container, and it will deliver 100 megawatts thermal of high temperature steam. So their business model is different in the sense that they are testing components as they are developing. So they don't design the entire reactor, build it, and then test it. They test each component as they progress. They've developed molten salt loops that they've sold around the world to other projects where they're using these loops and these can pumps to do research on molten salt. And they have completed a non-fission version of the reactor. So the heat comes from electrical heating and not from a nuclear reaction, but they're testing all the functions of the reactor in that way. I mentioned that they had this innovation of the sealless molten salt pump and the development of the ultra-pure salt to avoid the corrosion. And what they need now is, because Denmark is not a nuclear country, they need a host country for a 1 megawatt demonstration unit. And we had some discussions with them in Nexa, and it's part of Nexa's mandate to be able to host it in South Africa. But at the moment, they're looking at hosting it probably in the Netherlands. But we're keeping our thumbs crossed. It would be a very nice project to have in South Africa. So as you can see from the dashboard that I've gone through quickly, most of these projects are still very early in their basic design stage. Concepts are being proven in laboratory settings. So in this slide from David Nichols' previous presentation, we're here in the first value of death with most of them. The only one that I think has gone a bit further is Copenhagen Atomics, and I would put them in the second field where, because they've done validation and testing and they've had thousands of hours of testing of their pumps and valves and other equipment. So what are the themes? Several of these reactors are designed to burn uranium as a Kickstarter fuel and then to breed thorium. And the big advantage there is that the thorium transuranics have a much shorter half-life. So instead of storing the spent fuel for 100,000 years, you only need to store it 300 years. So that is one of the things that makes the use of thorium to breed uranium-233 so attractive. Many of them also have this big benefit of burning recycled spent fuel from the existing fleets of reactors, so reducing the overall nuclear waste inventory in the world. So depending on what application, you can have them using fast neutrons or thermal neutrons. Some are barge-based, but most of them are terrestrial designs. I mentioned already that they operated near, all of them operated near atmospheric pressure, avoiding the need for a heavy, expensive pressure vessel. They all operate with long fuel cycles. I think Copenhagen Atomics talks about 12 years. Others talk about 4 years. There is the big benefit of all of them is this idea of high outlet temperature that leads to flexibility and a lot of applications in the industry. In South Africa, for example, in Sasol, where they use a large amount of high temperature steam. And they range from about 60 megawatts thermal to the 1100, which are actually 500 megawatts thermal units. So, okay, that's my review. I think we can go on to questions.
Thank you. Looking at the questions, thank you, Derek. Very interesting. I feel there is vast potential in these, but I've got to. So while I'm waiting for someone to come with the question in the question box, as I'm missing it, I think the key question to me is most of the SMRs are based on machines or technology that is actually in some form or other run in a semi-commercial mode for some period of time. Molten-Salt's the one that hasn't and has some interesting curiosity. How long do you think I have to run the lead machine, whatever that is, until this could really be seen as being commercial? If I explain some more, if you look at pepper-bed reactors, for example, you could say, yeah, you haven't built a commercial one, but they have built and run the AVR in Germany for like 22 years. And I think the problems with molten salt are significant in terms of corrosion. So how long do you think I have to build and run one until industry will be confident to buy, you know, a block of 10?
Well, I think if one looks at the high temperature gas reactor in China, that one started up in 2022. They ran it for about a year and then declared that it's ready to be commercial. And they ran it for another year, and recently they announced that they're going to build 6 more of those. So based on that experience, I would say about 2 years. But that's just a judgment.
I'm going to come with a judgment in return. Sorry, and I'm just waiting for someone to come with a question because I'm not sure that's valid. I mean, the predecessor of the Chinese HTRPM was not the HTR-10, which was their test reactor. It was really the AVR and the THTR. And so I think that we've got significant corrosion problems. And I know that I'm going back to my own, well, our background, because you're involved as well at the time. The Inconel 600 story in light water reactors, where it took like probably 15 years from when they first thought they had solved the corrosion problem for realization that the widespread use of Inconel 600 was difficult in the present generation of plant. And I think the chemistry problems are much worse with molten salt. So that's my sort of thought process. But you're saying a couple of years. I'm looking out for, if you were going to go out tomorrow morning and order one, if you were Sasol's technology leadership and you were told to bet on one of these which one would you choose and why?
So
I'll give you, first of all, I'm looking for steam at 570 degrees centigrade to replace my current boilers at SAIEE. That's a specification for you very, very quickly. So which one would you go with? Both technology-wise and development.
Yeah, I would go with Copenhagen Atomics. They deliver, their business model is to deliver high temperature steam. They don't go beyond that second molten salt loop. In 2025, it's likely that they will do their demonstration for the 1 megawatt demonstration unit. That will run for a few months. It's not something that will run forever. It's just a test. And then thereafter, I think they claim they could get to an operating reactor probably by 2028 or so, but I would say 2030. But I would choose them because of the extensive testing that they've done on their components, on the experience they have with this ultra pure salt, and operating those molten salt test loops. And it fits into a 40-foot container. So the idea is that you prepare a seismic qualified slab somewhere in the SAIEE site, and you place this reactor close to where the boilers are, and you connect up your steam, high temperature steam. I think that would be a very convenient one. So you don't need a big containment building and all of that, but nevertheless, it's still a nuclear plant, so you will have to do site characterization, site licensing, and licensing of the device, and then the combined license. So one would have to go through with that. You could think that you would put these reactors on existing sites like Nexa and Coburg, but that wouldn't work for SAIEE because they need steam, they don't need electricity.
I think, just digress a little bit, and I must sort of put a bit of a comment that there has been a comment recently after discussions between Nexa and Eskom by the Eskom CEO and head of generation. They both made it separately that they're looking at the prospect of using Nexa as a vehicle to build the first of class of someone's design, and then to roll out SMRs onto the Highveld coal station, which I think is a very exciting idea. But that's not a steam-based thing. That's basically power. I think the other question I'd ask you is in terms of maintenance. Maintenance is often forgotten by clever designers. They design their reactor, and then someone asks you to maintain it 20 years later. It's nearly impossible. How do you reckon they're going to overcome the issues to do with contamination? Because I'm presuming that the primary circuit will get quite dirty with this kind of technology. What's the sort of maintenance regime being talked about?
Yeah, I think that's because these reactors, have you seen, are just in early concept phase, most of them. I don't think there much thought has been given to that. I know Copenhagen Atomics have worked on that, but I'm not really in a position to answer that question.
I've got a suspicion. I'm just going to keep going for a few more minutes, and then if you don't get any questions, I've got a suspicion that you've got to basically run these like you run uranium centrifuges, where you start it up, you set it up, it's designed to run theoretically forever, and basically if it stops working, you just turn it off, shut it off, and start another one. So the idea of smaller machines that are linked together makes a lot more sense to me than sort of 500 megawatt machines, electrical, because then your problem is that if you have doing maintenance in it will be quite challenging.
Yeah, so I mean, the example again is Copenhagen Atomics. They only have one moving part, and that's that pump.
Yeah.
And the idea is they would place the container down, and leave it to operate for 12 years. And at that point, they will come and fetch it and put another one down.
Yeah.
So you're moving into this idea of leasing the fuel, that you're just buying the electricity or the hot steam. You don't own the fuel nor the reactor, and the original supplier takes it away.
Yeah, the other, of course, nice thing about uranium, about the thorium fuel cycle, is it's almost impossible to make. It's got almost totally proliferation resistant, because making a nuclear weapon out of a thorium-232 cycle is I would suggest so close to zero you can ignore it. And that's the reason why it was never funded originally, because it didn't make bombs. It wasn't funded by the government in the 1950s and 60s. I'm a cynic in my old age. If you couldn't make a bomb or drive a nuclear submarine, nobody gave you money. I think we forget that was the motivation. I'm looking, I still see no questions in the question thing. Any other comments you want to make before we come to that? I'd look for any comment. Has anyone got any questions? I'm quite happy to, on anything to do with small modular reactors. I will not answer the question of who the next Minister of DMRE is and whether his policy on nuclear is. That's beyond my pay grade. That was a light-hearted comment, by the way. Okay, I'm going to pass us back. We've had no questions. I'm surprised at that. So excellent presentation. Thank you so much, Derek. I think it's a fascinating issue that we're staring at in the world, in terms of which of these technologies are going to work. And this is the one with the extreme level of, as no one's built one that's run more than a year or so, nobody knows the right answer. And, but anyway, with that, I'm going to pass back to, are you going to for final comments, Derek?
No, I think that the molten-salt reactors show a lot of promise, and but they're in the very early stage of development. So, but I do think that they could be very successful one day. I mean, I remember meeting you in Barcelona 20 years ago and talking about molten-salt reactors already back then.
Look, I mean, the thing is, someone's going to have the guts to go and build the first. I disagree with your 2 years. I think you're going to run one for about probably 10 years or so to make it larger. I think it's beyond the next generation of reactors. It's the one small modular reactor technology where when someone says we won't be commercially available in the 2040s, I tend to say on molten salt, I tend to agree with you. On the rest of the reactors, there's enough experience to say we know how to build liquid metal reactors. We know how to build other ones. Yeah, but it's interesting. But yeah, so I will leave it. Clearly, you've answered every question in the presentation. I'm going to pass back to Minx now. So Minx, the floor is yours.
Thank you very much. First of all, Derek, thank you very much for availing the time to do your very interesting presentation. And thank you, and travel safely back to Cape Town. David, once again, thank you very much for hosting this webinar. And most importantly, our attendees, thank you for joining us. We're looking forward to hosting you next time. Have a good day. Goodbye.
Thank you. Bye-bye.